Hello, my name is Kalyohan and welcome to this video. In this video I want to talk about the content of citric acid in lime juice. So to start off I want to talk about the experimental setup. And for this experiment, we did two different kind of titrations. The first one was just a titration using a pH identifier, so we were able to see when and where this pH is jumping from being an acid to a base. And then we did the same titration afterwards with a pH meter, so we were able to measure the pH throughout the whole titration. So to do this you need a burette where you add some sodium hydroxide, which is what we were titrating with, 0.100 molar sodium hydroxide. Then you need a burette holder and then a stand to hold the burette holder, so you can keep the burette holder in place and measure throughout the whole titration. When you're doing with the pH meter, you need something to hold the pH meter in the solution so it can measure the pH throughout the whole titration. And then you need a pipette, 25 milliliter, and a pipette pump to add 25 milliliter of our citric acid into a 200 milliliter beaker. You need to place that on a magnetic stir, put in a magnet so you're able to stir it throughout the titration. On the macroscopic observations of this experiment, when we are doing this with a pH identifier, we were using phenolphthalein, which is turning from colorless to pink when going from an acid to base. So when going from acid to no acid in the solution. So when we are titrating with sodium hydroxide, and that has a reactant called acid, the phenolphthalein will turn the solution pink. And we are doing that from both the lemon juice and the lime juice. So we were able to see if it's happening in both of them. Our results from this lemon and lime juice experiments was when we were doing with a pH meter. We got this beautiful graph over here, which you can see, and the blue one is for citric acid and the red one is from lime juice. To look at the reaction schemes for the citric acid reaction, we have the first endpoint reaction here. The reason I say first is because we actually have three endpoints in this reaction. So the first reaction is going from citric acid to citric acid minus, and minus comes from this OH group reacting with sodium hydroxide, creating an O minus over here. Then we have the second endpoint reaction is citric acid minus reacting to citric acid double minus, making this OH group here going to this minus over here. And then the third reaction is this citric acid double minus going to citric acid triple minus, making this OH group here to this O minus over here. Then we can see the three different endpoints in the reaction. We have the third one here. That is the third endpoint we are able to see on the graph. And then we can calculate to these two endpoints. These two endpoints is calculated from, I will explain that later in the video, but they are roughly placed here on the graph. So to get the pKa for the first endpoint, then you need to have the volume of the sodium hydroxide added to the solution. For the third endpoint, meaning that we added 19.4 milliliters to the solution, you divide that by 3, getting 6.47 milliliters. This means that we have added 6.47 milliliters to get the first endpoint of our reaction. We divide that 6.47 milliliters by 2, getting 3.235, because when you need to calculate the pKa of an endpoint, you need to divide the endpoint by 2 and then look at the pH on the y-axis of the graph. We didn't have a point saying 3.235, so we rounded that to 3 milliliters and then got a pKa of 3.23. For the second endpoint, we did roughly the same. We just timed the 2 up here. So we timed the 19.4 milliliters divided by 3, then timed that by 2, getting 12.94, meaning that here in 12.94 milliliters we will have the second endpoint. To now get the middle of the first endpoint and the second endpoint, we need to take the average of these two. So we plus 12.94 plus that was 6.47, divide that by 2, getting 9.01 milliliters, and equal that to 9.5 because of the same reason as before, giving us a pKa of 4.62. And for the third endpoint, we did roughly the same. We took the average of the second endpoint plus with the third endpoint, and then we took the average of that, getting 16.17, and we rounded as to 16.25 because of the same reasons as before, giving us a pKa of 6.16. Now we need to calculate the concentration of citric acid in citrus juice. And to do this, we first need this amount of hydroxide ions in the solution, in the sodium hydroxide, and that is equal to 3 times the solution of citric acid. Because we have 3 endpoints, we will have 3 times as much sodium hydroxide as the citric acid in our solution. So we need to know the amount of it, and to know this we need the concentration reaction, which is the concentration equals the amount divided by the volume. We rewrite this to get the amount equals to the concentration times the volume. Now we can get the amount of the sodium, the hydroxide ions, taking the end point volume, and which is 19.4, and times that with 0.100 molar. But because of the units don't equal out, we need to times the 19.4 milliliters with 1,000 to get it to liters instead. So it makes 0.09194 liters times up with 0.100 molar, and molar is the same as moles per liter, and therefore we can get a result saying 0.00194 moles. That is our amount of hydroxide ions in this sodium hydroxide. Now we are able to calculate the concentration, not the concentration, but calculate the amount of citric acid. Then we take the amount of sodium hydroxide ions, divide that by 3, giving us 0.009194 molar divided by 3, giving us 0.000647 moles. So our amount of citric acid is 7.000647 moles. Now we can calculate the concentration of citric acid, which is the concentration formula we use from up here. And then we take the amount of citric acid divided by the volume of citric acid. So it's 0.000647 moles divided by 0.025 liters. And the reason for this, we added 25 milliliters of the citric acid, but 25 milliliters is equal to 0.025 liters, and again it's because of the units. So our concentration of citric acid will therefore give us 0.259 moles per liter. Now we want to calculate the pH for this for the first endpoint. And to do this, we need the concentration, and then we need to get Mabel to solve an equation for us, which we can't do by hand, which is called Ka equals to x squared divided by concentration of our substance minus x. Then we set Mabel to calculate this for her, giving us an x is the amount of 830 plus, giving us 0.004026. And when we calculate this, it gives us a Ka value of 7.41 times 10 in minus 4 molar. Now we can calculate the pH by taking the minus logarithm of 830 plus, giving us the minus logarithm of x, which is minus logarithm of 0.004026, giving us a pH of 2.395, which is fairly close to a pH from the table that was 2.6. To calculate from the second endpoint, we again need the concentration, but in this we need another pH formula, which is called pH equals to 1 divided by 2 times times the pKa minus logarithm to the concentration of your substance. So in this one, it was 1 divided by 2 times 6.16 minus logarithm of 0.0259 molar, and giving us a 3.87. But our pH on the table was 5.41, which is not that good compared to the other one. Then we have the citric acid comparison. For the pKa from our book and from what we calculated, they are all very, very close to each other. and giving us roughly 0.1 difference in them. And the reason for this difference is because of the experimental errors there are in the experiment. For example, you can't measure completely with your eye, so when you look at the burette, you can measure completely how much you actually added to the solution. So, are there citric acid in lime juice? The big question. Yes, there is. You can see the two graphs is almost identical. The only difference is that the lime juice is shifted a little to the left. And the reason for this is the concentration of citric acid in lime juice is not as concentrated as it is in citric acid. So therefore it will be shifted a little to the left, and the start pH will be a little above the citric acid. So therefore, to conclude on this experiment, we had a very successful experiment, giving us exactly the result that we wanted to have. That there is citric acid in lime juice. So when you're drinking lime juice, you're actually also drinking a little citric acid, but don't worry, it's not dangerous. So yes, thank you for watching this video. I really hope you enjoyed it, and I will hopefully see you in the next one. Bye.